Hi everyone, welcome to part 4 of lecture 9. And in this lecture, we will try to understand why the moment generating function is important and how we can use that one. As I said in the previous part, instead of memorizing how we can calculate the moment generating function and what is the exact formulation of the moment generating function for a special distribution is not important. But the important thing is to understand the basic foundation behind that function, okay? And from this perspective, we have two main reasons. And the first one is not too important, but it is good to make all these things more clear, more concrete, okay? And the second one is much more important. But let's start with the first one. And before going to the details, let me remind you something. Remember that the sum of x to the k divided by k factorial is equal to a to the x, right? So for the and k from 0 to infinite. And let's say if k is 0, that means that will be 1. And if k is 1, that will be x. If k is 2, that will be x squared divided by 2 factorial. And so on, right? So remember, what was the moment generating function? That was the expected value of e to the tx, right? So instead of that x, if we just put the tx, we can say that e to the tx will be equal to 1 plus tx. As I said, we will just put the tx instead of x, plus tx squared divided by 2 factorial plus tx cubed divided by 3 factorial, etc. Okay? So the moment generating function, which is equal to expected value of e to the tx, and that will be equal to 1 plus t times expected value of x, because here the x is random variable, so we can take the expected value of x, but t is constant, that can be the outside of the expectation, and plus t squared times expected value of x squared divided by 2 factorial, and so on. So let's take the derivative of the moment generating function. So this guy will be vanished, and for this one we will end it up with expected value of x, right? And because that is a 1, and it will be, sorry, yeah, that will be 1, and that will be 1 times the expected value of x. Okay, so we will left with expected value of x. For this one, we will left with t times expected value of x squared, right? For this one, we will left with t squared divided by 2 factorial times expected value of x cubed, etc. And I hope you see the pattern that power cancel the first term of the factorial in each step, okay? And that is the first derivative of the moment generating function, right? And let's evaluate this derivative when for the t is equal to 0. So that will be 0, that will be 0. So the a return include every term with the coefficient with the t will be 0. So I will left with the expected value of x, right? So the first derivative of the moment generating function evaluated at the t is equal to 0 will give us the first moment, the expected value of x, okay? If we derivative, if we derivative this guy, this whole guy again, so that will be the second derivative of the moment generating function. For this one, that will be vanished, and that one will be expected value of x squared. This guy will be expected, uh, yeah, this guy will be t times expected value of x cubed, etc. Again, we have same pattern. The power cancel the first term of the factorial in each summation, okay, in each term. And imagine that again we evaluated the second derivative of the moment generating function in t is equal to 0. That will give us the expected value of x squared, right? Because that will be 0 because we have t here. We have t here, that will be 0. We have t here, that will be 0. And we will left with the expected value of x squared. So that's mean the second derivative of the moment generating function evaluated at the t is equal to 0 will give us the expected value of x squared, which is the second moment. So we can generalize these things. If we want to calculate the nth moment of a random variable, we need to take the nth derivative of the moment generating function, and we need to evaluate that one at the t is equal to 0. Okay, so this is the general rule, and these things may these rules can make some things much more easier. Okay, let's look an example to understand how we can use the moment generating function. Okay, now we know that the moment generating function of a gamma distribution is this one. We just seen that in the previous part, and let's see how we can use that one. Imagine that we are asked to calculate the variance of the gamma distribution, which is equal to e to the expected value of x squared minus expected value of x squared. So that is the second moment, and that is the first moment. And we know that, we just learned that, how we can calculate the first moment, second moment, third moment, etc. Well, how? To calculate the first moment, we need to take the derivative of the moment generating function and evaluate it at t is equal to 0. Okay, now let's take the derivative of this guy. Let me take that one and go a new page. Okay. So first, we need to take the derivative of the whole things. That will be alpha times lambda divided by lambda minus t to the alpha minus 1, and times the derivative of the inside, right? But for the inside, we need to use this rule, which is the derivative of f of x and the derivative of the g of x, which is equal to the derivative of f of x times g of x minus the derivative of the g of x times f of x, the square of g of x. Okay. Now let's say that is our f of x, and that is the g of x. So let's start from here. What is the derivative of that one with respect to t, which is 0? So these guys, these whole things will be 0, right? Okay. So what is that will be 0. So minus, let's calculate that one, which is the derivative of this one, the g of x, which is minus 1, right? Minus 1 times f of x, which is lambda. Okay, and divided by the square of the g of x, which is lambda minus t, and lambda minus t squared. So these guys, let me write all these things here again. That is alpha times lambda minus lambda over lambda minus t to the alpha minus 1 times that will be plus lambda divided by lambda minus t squared. Okay. So, and this guy can be written as lambda to the alpha minus 1 divided by lambda minus t to the alpha minus 1. Okay. So if I add the power of this two guy, I will get um, the lambda to the alpha. And if I sum the power of this two guy, I will get lambda minus t to the alpha plus 1 and times alpha. That is coming from this one. Okay, that is the first derivative of the moment generating function. But to calculate the first moment, we have to evaluate this one at t is equal to 0. So that will be the lambda to the alpha divided by lambda minus 0 to the alpha plus 1 times alpha. So this part will be lambda. So this will equal to lambda to the alpha divided by lambda to the alpha times lambda times alpha. So these guys will be cancel each other, and I will end up with lambda over alpha over lambda. So this is the first moment of the gamma distribution, and which is expected value of x. Okay. Now, which is alpha over lambda. So we have calculated that one. But now let's look at the second moment. That's mean we have to take the derivative of this guy, right? Because that is the first derivative of the moment generating function, and we have to derivative it again. So let's take this guy. Okay, a new page, and we will do the same thing. Again, imagine that is that is our f of x, and let's say that is the g of x. Okay. So what is the derivative of the first, the f of x, which is 0, right? So that would be 0. So I will apply the same strategy as I applied here. Okay, here. So 0 minus derivative of this guy. Okay, first derivative of this guy times f of x. So what is the derivative of this guy? First, take the whole derivative, which will be alpha plus 1 times lambda minus t to the alpha times derivative of the inside, which is minus 1, right? So this guy will be minus alpha plus 1 times lambda minus t to the alpha. That is the derivative of the g of x, okay, which is minus alpha plus 1 times lambda minus t to the alpha and times f of x, which is lambda to the alpha. Okay. And we need to take the square of g of x, which is lambda minus t to alpha plus 2. Okay. So that's one. These guys will be plus sign, and that will be alpha plus 1 times lambda minus t to the alpha times lambda to the alpha divided by lambda minus t to the 2 alpha plus 2. So this is the second derivative of the moment generating function, but we need to evaluate it at t is equal to 0, right? So this guy will be alpha plus 1 times lambda to the alpha, because t t is 0 times lambda to the alpha and divided by, again, that will be lambda to the 2 alpha plus 2. Okay, so this 2 guys will cancel with this one, and I will ended up with um, alpha plus 1 divided by lambda 2, but I have one alpha here, right? One alpha here. Alpha times alpha plus 1 divided by lambda square. Okay, so that is the second moment of the gamma distribution. And if we put what we found here, we will get alpha over lambda square. So in the previous lectures, remember that to calculate the variances, we do some integrals, some complicated works, right? But here it is respectively much easier. So therefore, we can use the moment generating function to do such calculations. Okay, so that is the first reason why the moment generating function is or can be much more useful. But there is much more important reasons. So let me explain it. If you have two random variables, let's say x and y, and if you know that the expected value of x and expected value of y is equal, also the expected value of x squared and expected value of y squared is the same, and all the expected value of the x cubed, y cubed, everything is same. Still, you cannot claim that x and y are identically distributed. So what I mean, you cannot claim that they are coming from the same distribution, okay? But if you have two random variables, x and y, and if you know that the moment generating function of both random variable for each t is equal, then you can claim that x and y are identical distributed. That means they are coming from the same distribution. That means the MGP, the moment generating function, contains all the information what the CDF contains. Okay, this property enable us to figure out the distribution of functions of a random variable. Okay, most notably the sum of the random variables, we will see it. So that's mean in summary, if you can compute the MGP, the moment generating function of a random variable x with an unknown distribution, and if you recognize that that is a known MGP, that's mean you know the distribution of x, because the MGP of a Poisson distribution and MGP of the gamma distribution cannot be same. Okay, they are unique. That's why if you know the MGP, that means you know the distribution of that random variable. That's why the moment generating function is really, really important. Okay, let's look at an example and assume that we have a random variable x, which is normally distributed with the parameters mu and sigma square. And the question is, what is the distribution of y, which is equal to a times x plus b? We can find the distribution of this guy by using the conventional way, and we did it, and that is, we know that that's the normal distributor. But also we can use the moment generating function. How? The moment generating function of y at the point t, which is equal to the expected value of e to the ty, right? We know that. We know this part. That is simple definition of the moment generating function. And instead of y, let's write a times x plus b, and we can rewrite this part as e to the atx times e to the tb. Okay, so until that point is clear, we just do some simple math, and that is constant. That is not about random variable, so that can go outside the expectation. So that will be e to the tb times expected value of e to the atx. Okay, and remember that the moment generating function of t, which is equal to the expected value of e to the tx, right? If this is the case, I can simply say that the moment generating function of at, which is equal to expected value of e to the atx, right? I just used at instead of t. So here, so I can say that the expected value of e to the atx is equal to the moment generating function of at, right? Moment generating function of at. And I know that the x is normally distributed. And remember that the moment generating function of the normal distribution is, if I'm not wrong, which is e to the mu t times e to the sigma square t square divided by 2. Okay. So instead of t, I will just write at, because instead of t, the moment generating function of t, we have the moment generating function of at. So that will be e to the mu at times e to the sigma square a square t square divided by 2. Okay, that is coming from this. So I can rewrite this part as e to the a mu plus b times t, okay, and times e to the a sigma square times t square divided by 2. I rewrite this on purpose because which has same pattern with this one with different parameters. How? Instead of mu, I have a times mu plus b, and instead of sigma, I have a times sigma. So that's why we can say that that new random variable y has a normal distribution with the parameters a times mu plus b and a square times sigma square. Okay, so we just deduce these points by using the moment generating function. Okay, that is one of the way to using the moment generating function. So before continue, let me give you some quick piece of information, which is called the sum of independent random variables. Assume that we have a random variable, and that random variable is the sum of different number of variables, and those variables are independent. Okay, so these x's are independent. So x1 is independent from others, x2 independent from others, and summation of them will give us a new random variable, which is y. We have the moment generating function of y at point t, which is equal to expected value of e to the ty, and that is equal to, instead of y, I can use that summation. So that will be e to the t times x1 plus t times x2 plus until t times xn. Okay, and I can write these guys as a product. So that will be expected value of e to the t x1 times e to the t x2 times e to the t x3 until e to the t xn. Okay, because these random variables are independent, okay, independent, I can write these guys as expected value of e to the t x1 times expected value of e to the t x2. Okay, we seen this equality in the previous lectures, and also we will see in the I think in the last lectures. But if these random variables are independent, expected of the multiplication of those random variables is equal to multiplication of the expected of them. Okay, so that is the moment generating function of x1, right? And that is the moment generating function of x2. So that is equal to the multiplication of the moment generating functions. So the moment generating functions of a sum of independent random variable is the product of individual moment generating functions. Okay. So again, the MGF of sum of independent random variables, okay, sum of independent random variables is the product of the individual moment generating function, because the moment generating function of y is the multiplication of the individual one, and y is the sum of those individual ones. Also, if xi and I from 1 to n are identically distributed, so they are independent and identically distributed, we have in general form the moment generating function of y will be the moment generating function of x to the n. Okay, if they are identically if they are independent and identically distributed, we can use this equation, this equality. Okay, because these guys will be same. If they are independent and identical, that means they are coming from the same distribution. And remember that a specific distribution has a unique the moment generating function that is the same. So the MGF will be same for all those random variables because they are coming from the same distribution. That's why we can take the power of it. Okay. Okay, let's look at another example. Assume that x1 is normally distributed with the parameters mu1 and sigma1 square, and x2 is normally distributed with the parameter mu2 and sigma2 square. What is the distribution of y, which is equal to x1 plus x2 if x1 and x2 are independent? We know that if they are independent, the moment generating function of y, and y is the sum of in some other individual random variable, is equal to the moment generating function of those individual random variables. So, which is the moment generating function of y will be equal to moment generating function of x1 times moment generating function of x2. And we know the moment generating function of the normal distribution. We know that one. We just put the parameters e to the mu1 times t times e to the sigma square 1 times t squared divided by 2, and we did the same thing for the second one. Okay, and at the end we get e to the mu1 plus mu2 times t times e to the sigma1 squared times sigma2 squared times t squared divided by 2. That means the new variable y has a normally distributed with the parameters mu1 plus mu2 and sigma1 squared plus sigma2 squares. Okay, so that is how we can use the MGF. Now let's look at another example. What is the distribution of y, which is the sum of some random variables, and those random variables are independent, identically distributed with exponential with the rate lambda. Okay, remember that one, which is we just covered in the previous lectures, the arrival time of the Kate customer in a Poisson process. Okay, so remember that the moment generating function of y, and y is the sum of some other random variables, is the moment generating function of those individual independent random variables, the product of those independent random variables. Okay, so that the moment generating function of y will be equal to the moment generating function of first random variable times moment generating function of the second random variables, and all those random variables are independent from each other. But in this case, they are also identical. That's why the moment generating function of all those random variables is same, which is lambda over lambda minus t. We know that we calculated the previous part, which is lambda minus lambda divided lambda minus t, and it is same all random variables. So we can simply calculate it lambda over lambda minus t to the k, because we have k random variable. Okay, and that is the moment generating function of y. So that is the moment generating function of the gamma distribution with the rate lambda and the shape parameter alpha is equal to k. Okay, so again, by using the sum of independent random variables rules in terms of moment generating function, we found that that new random variable is coming from a gamma distribution with the given parameters. Okay, so that is how we can use the gamma distribution. Okay, so we have another example. Assume that x1 is Poisson with rate lambda 1 and the x2 is Poisson again with the rate lambda 2. So what is the distribution of y, which is equal to x1 plus x2 if x1 and x2 are independent? Again, we have the same thing. The moment generating function of a random variable, which is sum of some other independent random variables, is the product of those product of the moment generating function of those random variables. Okay, so in this case, the moment generating function of y will be the moment generating function of x1 times moment generating function of x2. And we know that they are coming from the Poisson distribution. And remember, the moment generating function of the Poisson distribution is e to the minus lambda times 1 minus e to the t. And in the first random variable has the parameter lambda 1. So we just put the lambda 1 here, and we did same thing here, which is we just put the lambda 2 into the lambda. Okay, so remember the moment generating function of the Poisson distribution is e to the minus lambda times 1 minus e to the t. Okay, so we have ended up with e to the minus lambda 1 plus lambda 2 times 1 minus e to the t. Okay, e to the minus lambda 1 plus lambda 2 times 1 minus e to t. So we just recognize this is that what we found is the moment generating function of the Poisson random variable with the rate lambda 1 plus lambda 2. Okay, that is same. Just put here, instead of lambda, put lambda 1 plus lambda 2. Okay, so we can conclude that y is also coming from a Poisson distribution. Okay. Okay, that is end of lecture 9. And in this part, we have seen how we can use the moment generating function and also how it can be more useful than the CDF. Okay. And sometimes, instead of doing some more complex calculations, you can simply use the moment generating function to do it in an easy way. For example, to calculate the variance, instead of doing some integral or some a tedious job, you can simply calculate or simply use the moment generating function. Okay, so that is the end of lecture, and thanks for watching.